Have you ever really stopped to think about the computer sitting on your desk versus the quantum computers that are starting to change, well, everything? I mean, they both compute, sure, but the way they actually think is just on a completely different planet. It's like comparing a simple light switch to a massive, unpredictable thundercloud. So yeah, let's dive into exactly what that means. All right, here's our game plan. We're going to start with the solid, dependable world of classical bits. Then, we'll jump into the deep end with the wild possibilities of qubits. We'll find out where their incredible power comes from, put them head-to-head with today's CPUs, and then we'll look at how they're actually going to work together in the future. Okay, first up, let's ground ourselves in the familiar. We're talking about the world of classical computing, and the one tiny thing that makes it all work. You know, every single thing you do on a computer, every video you stream, every message you send, every photo you scroll past, it all boils down to trillions and trillions of super simple yes or no choices happening at an insane speed. There's no gray area, no maybe. It's just a clear, definite answer.
And that fundamental choice, that's the classical bit. It's basically the atom of our digital world. Physically, it's just a tiny transistor that's either on or off. Logically, that means it's what we call deterministic. It's always a 0 or a 1. It can't be anything in between, and it definitely can't be both at the same time. This absolute certainty is the bedrock of all computing as we know it.
So, that's the world of certainty. It's reliable, it's solid. Now, let's leave all that behind and get a little weird as we step into the quantum realm. See, quantum computing kicks off by asking a really mind-bending question. What if, instead of being forced to choose between yes and no, a single unit of information could actually hold a little bit of yes and a little bit of no at the exact same time?
And that brings us to the qubit. While a bit has to pick a side, a qubit just doesn't. Thanks to a wild property of quantum mechanics called superposition, a qubit can be a 0, a 1, or a whole spectrum of possibilities in between, all at once. It's in this fuzzy, probabilistic state right up until the moment you measure it.
This is probably the best analogy you'll find. A classical bit is just like a light switch. It's either on or it's off. Simple, certain. A qubit, on the other hand, is like a dimmer switch. It can be all the way on, all the way off, or an infinite number of shades of brightness in between. Its actual value is just a probability until you flick the switch and look at it. Okay, so a qubit can hold more information than a bit. Cool, but why is that such a game changer? Why does it lead to this unbelievable jump in computing power? Well, let's look at the engine that drives it all, this thing called superposition.
And here it is, the secret sauce, exponential scaling. Think about it. If you have, say, 8 classical bits, they can represent exactly one number at any given moment. But 8 qubits, because each one is in that state of superposition, can represent 2 to the power of 8. That's 256, all at the exact same time. Add just one more qubit, and you double it to 512. That's what they call quantum parallelism. And this is where the numbers just get absolutely mind-boggling. It's not just doubling, it's an explosion. With just 300 qubits, a quantum computer could explore a number of possibilities at the same time that is larger than the number of atoms in the entire known universe. Let that sink in. That's a scale that classical computers can't just catch up to. It's fundamentally unreachable for them. So how does a quantum computer actually harness this power? Well, you can think of it as a 3-step dance. First, you put all your qubits into superposition. So now you're basically looking at every possible answer to your problem all at once. Second, you use what are called quantum gates to entangle the qubits, linking their destinies together, and then use interference to make the wrong answers cancel each other out, while the right answers get stronger. And finally, you measure it. The whole system collapses out of that fuzzy quantum state, and the one answer with the highest probability is what you get.
Okay, we've seen they think in fundamentally different ways. So let's put the classical CPU and the quantum QPU side by side. But remember, this isn't about which one is better. This is about having 2 very different tools for 2 very different jobs.
This table really lays it all out. Your CPU uses silicon transistors. A QPU might use superconducting circuits or even trapped particles of light. The CPU's logic is totally deterministic, running on simple Boolean algebra, and or not. The QPU is probabilistic, running on the much more complex math of linear algebra. But that last row, that's the kicker. A CPU's power is linear. Add more cores, get more power. A QPU's is exponential.
And it's important to realize that QPU isn't just one thing. There are a bunch of different ways to actually build a qubit. Superconducting qubits are super fast, but you have to keep them colder than deep space.
Trapped ions are more stable, but they're also slower. Then you have things like photonic qubits that can run at room temperature. It's a huge engineering race right now, with everyone making different bets on what will scale the best.
So if these QPUs are so ridiculously powerful, does that mean they're going to replace the CPU in your laptop anytime soon? The short answer is a definite no. So let's look at what the future actually looks like, a hybrid computing future.
This quote right here just nails it. The future isn't about one replacing the other, it's about integration. It's about getting the classical silicon workhorse to work hand in hand with the new quantum engine.
And here's why that makes perfect sense. They are good at completely different things. Your CPU is the master of all the everyday stuff, email, websites, spreadsheets. It's built for clear, sequential, deterministic logic. QPUs, on the other hand, are specialists. They are built for the kinds of problems so massive that no classical computer could ever solve them. Things like designing new drugs by simulating molecules or cracking today's toughest encryption.
The way this actually works in the real world is that a quantum computer isn't some standalone machine. The QPU itself acts more like a specialized accelerator, kind of like how a GPU accelerates graphics. It gets plugged into a giant classical supercomputer. The classical machine handles all the normal stuff, hands off a specific, gnarly problem to the QPU, and then takes the probabilistic answer it gets back and makes sense of it.
So, there you have it. We've gone from the absolute certainty of the bit to the infinite possibilities of the qubit. We're in the process of building these incredible new engines that think in a way that's totally alien to us. And really, the only question left is, with these powerful new tools in our hands, which of today's impossible problems are we going to solve first?